Let's look at some properties of stars. As we look at stars, we actually see that they have different colors. It is sometimes a little bit hard because they're all glowing in the dark sky, but stars do have different colors. For example, in the constellation of Orion, the star in the top left that would make up Orion's left shoulder is actually reddish in color, and the star in the bottom right is bluish in color. Well, the color of a star is actually related to its temperature. If you remember way back when we were talking about light and temperature, every object that has a temperature is giving off some light. For stars, they're hot enough, they're actually giving off visible light. As objects begin to heat up, then they start giving off the lowest energy light first, which is red. So objects that are glowing start out red. Then, as they continue to heat, they'll transition from red to orange, then to yellow, then to white, and then finally to blue. An object that is so hot it is glowing blue is very, very hot. Do not touch it. So a blue star is much hotter than a red star. Red stars are relatively cool, and blue stars are hot. Now notice I say red is relatively cool. If it's so hot that it's glowing red, still don't touch it. It's still too hot. Another thing that we use to help us measure and understand stars is the brightness and the luminosity. The apparent brightness, or sometimes we just simply say the brightness, is how the star appears to us, or in other words, the amount of light that we actually receive from the star. What does it look like? The luminosity is the intrinsic brightness, or in other words, how much energy the star is actually giving off. The luminosity isn't going to change based off of distance from the star. No matter where the star is, it's going to give off the same amount of light. However, the apparent brightness is going to change. As the light leaves the star, it naturally spreads out as the surface area of a sphere, which means that the farther away the star is, the fainter it's going to appear, the smaller its apparent brightness. And you can kind of think about this with light bulbs. At least when I go to the store to help me figure out how much light a light bulb gives off, I usually look at the wattage. I realize that new light bulbs have things like lumens and lux and other measurements, but I'm old school, I still look at the watts. And so the watts tells us how much light the star or the light bulb is actually going to give off. A 75 watt bulb doesn't give off as much energy as a 100 watt light bulb. Okay, so no matter where the 100 watt light bulb is, whether it's close or far away, it's still giving off the same amount of light. However, depending on how far away or how close it is, changes how much of that light you get. If you've got that 100 watt light bulb, say in a vanity in the bathroom, near your mirror so that you can see, it's got a lot of light. You can see everything very, very clearly. But if you take that same 100 watt light bulb and you put it several miles away, you're not going to be able to use it to actually see anything. You're not getting nearly enough light. So the luminosity is the watts. It's giving off the same amount of energy no matter where it is. The brightness is how much of that we get. So we do actually have a relationship between the brightness, the luminosity, and the distance. So B here is the brightness, and this is related to the star's luminosity divided by the distance squared. So this is another one of those inverse square laws, like we saw previously with gravity and the electromagnetic force. So the farther away the object is, the less bright it's going to appear. Now, we often compare stars to the sun. Anytime you see something where we have a subscript of sun, that means the property of the sun. So, for example, L sun is the luminosity of the sun. Here is our first clicker question. We measure the sun's luminosity, L sun. If we were on a spaceship twice as far away from the sun, its apparent brightness would appear A, the same, B, half as much, C, 1/4 as much, or D, 4 times as much. Go ahead and think about it, and we'll discuss in just a bit. All right, so if you remember, brightness follows an inverse square, which means if you're twice as far away, 2 squared is 4, but it's inverse, which means it's on the bottom. So it's 1/4. So it would be 1/4 as much. So the correct answer is C. Now, one way that we have to help us understand what's going on with stars is the Hertzsprung-Russell diagram. This is similar in some ways to the periodic table. Just like you don't memorize the periodic table, you don't memorize the HR diagram, but understanding how to read it really gives an astronomer a lot of information about the stars that we're looking at. So in the Hertzsprung-Russell diagram, we actually just say HR for short, because that's a lot easier to say than Hertzsprung-Russell. Along the bottom, we have temperature, and then up and down, we have luminosity. Now, something I want to point out is notice our temperature scale. It is hot on the left and cool on the right. So it is blue on the left and red on the right. This is backwards from the way that we normally think. Usually we have increasing numbers as we go left to right. In this case, we have decreasing numbers as we go left to right. So it's hot on the left, cool on the right. Up and down is the luminosity, how much energy the star is actually giving off. And in this case, it's exactly what you expect, with low luminosity on the bottom and high luminosity on the top. Well, as we take stars and we start plotting them based on their temperature versus luminosity, we start to find some interesting groupings. We have this diagonal line going along the middle. This is referred to as the main sequence of stars because about 90% of all stars fall somewhere along that line. We have another group in the top right. These are known as the giants and supergiants. Then we have another group in the bottom left. These are known as white dwarfs. Now, the luminosity is actually related to the temperature of the star. The hotter an object is, the more light it gives off, but it is also related to the radius, how big the star is. An object that is bigger is able to give off more light and is therefore going to be more luminous. So the luminosity of a star is related to its radius squared and its temperature to the fourth. So what this means is if we can determine a star's luminosity and we can determine its temperature, that allows us to know what its radius is. So as we start to apply this, if we look at the HR diagram, we have temperature versus luminosity. This means that we can actually figure out the size of a star simply by where it is located on the HR diagram. These stars in the bottom left, they're very, very hot, which means higher luminosity, but we see they have a very low luminosity. What this means is that their radius has to be very, very small. Okay, so white dwarfs, from what we can tell, are about the size of the Earth. Not the Sun, not Jupiter, the Earth. In other words, they are very, very small for stars. As we go from the bottom left up towards the top right, the stars in the top right have very, very high luminosity and very, very low temperature. What this means is their radius must be very, very large. That's why we refer to these as giants and supergiants. Giant stars have radiuses that are hundreds of times larger than our sun. Supergiants have radiuses that are thousands of times larger than our sun. In other words, these are really, really big stars. Here is our second clicker question. A dying star that has collapsed to a small size and is still very hot would appear in which part of the HR diagram? A, lower left, B, upper left, C, lower right, or D, upper right? Go ahead and think about it and we'll discuss in just a bit. All right, so we know that it is going to have a small size, but is very, very hot. If it's hot, it's going to be on the far left side, because left is hot. And then if it has if it's very small, it's also going to have a relatively small luminosity, so it's going to be near the bottom. So the correct answer is A, lower left. Such as these stars are actually white dwarfs. We'll talk more about them in a bit.